Hello, my name is Jose, and in this video we're going to be replicating the synthetic control method for comparative case studies. In this case, the application is estimating the effect of California's tobacco control program. This is a paper that it's pretty much a seminal paper, authored by Alberto Abadie, Alexis Diamond, and Jens Hainmueller. Alberto Abadie introduced the synthetic control method in 2003 in this other paper, The Economic Costs of Conflict, a case study of the Basque Country, authored by Alberto Abadie and Javier Gardeazabal. But we're not going to be focusing on this paper, and it's worth mentioning, perhaps, noting that the most cited paper in the synthetic control literature is the one of California, the one that estimates the effect of California's tobacco control program. I would say that's arguably because this application is so good and was expressed and presented so eloquently in this paper. I think this paper is perhaps the most straightforward, intuitive, easy to understand, and illustrative, high-quality application of the synthetic control method for anyone who wants to learn how to use the method and understand it. I would say that even non-technical people who skim this paper can get a very good grasp about how the method basically works, and the ones who want to learn to apply it, I think can also learn a lot of the tips, because this paper contains a lot of good tips that we're going to be covering. All right, so we're going to be using R. In particular, we're going to be using the Synth package for R. This package is the one that was authored by the same authors of the paper, which I think it's just perhaps great. There are a lot of applications over the internet using Python, but we're going to stick with the package that was actually used, created by the authors of the same paper. All right? So let's get started. Assumptions. You have installed R. There are many videos over the internet about how to do that. So that's very straightforward. Create a script. One thing before we get started, I'm going to be making perhaps a few mistakes here and there, or perhaps hesitating about how to proceed here or there. And that's to be expected because I'm going to be thinking out loud. I think the greatest advantage of video tutorials is seeing the author of the video struggling. I think that's how I've learned the most in the past, and I hope that's the best way to teach as well. Okay, first things first, install packages. In this case, the synth package for R, which we're going to be using. I already have it installed, but I can always rerun this command and it's going to be fine. You only have to run it once. Assuming you already run it in the past, you could possibly perhaps get rid of it. Yeah, so we call the library synth in this case. We load the library and we need to load the data. Yeah, that's very important. I'm going to be publishing a repository where you can download this data, in fact. And let's see, I want to show it on my screen. That's okay. So here you're going to have the data. I'm going to be sharing this link with you guys. Yeah, so all right, yeah, so as I said, we copy paste the link for our data. California data URL. All right. Excuse the long name. It's for search engine optimization purposes when we publish it on GitHub. We need the data frame, California data frame, read CSV. We can put the URL, and here we can check that we have the data frame loaded. I wonder if this looks as it's supposed to look. File tree. This doesn't look right. Yeah, you know, first example of how to struggle in a live video. Right, so first issue, we need the raw link, you know. Right. You know, the reason I noticed this was not looking right is because usually when you load a CSV, it doesn't look like this. Like you're able to see like the columns, you know, of your CSV file. And in this case, I can't see them. So that's how I realized that something was off, you know, because I see a lot of weird stuff here that shouldn't be there. So that's the first mistake that I made on the live video. You know, when on GitHub, when you are loading a CSV file from a repository or a GitHub guest, you know, you should do the raw version. So it's raw.githubusercontent.com. So we do that instead. You see? Now we have the California data frame properly loaded here. State, a state name, and the year, sale, income, age, 15 to 24, and the retail price. It's important for you to actually get familiarized with the paper. The synthetic control method uses the concept of predictors. Excuse my voice, I'm a little sick. This is such a shame given that I'm recording a live video. But we'll do it still. So I suppose we should go a little bit over a few definitions about the synthetic control method. The idea behind the synthetic control approach is that a combination of units often provides a better comparison for the unit exposed to the intervention than any single unit alone. So what does that mean? So if you see here in the first figure, figure 1 of the paper, we see here the trend of per capita cigarette sales in packs, right, over the decades. 1970, 1975, 1980, 1985. The solid line is California in figure 1. And you can see that Proposition 99, which was pretty much a tax. It was a tax on cigarettes. So Proposition 99 was implemented, and we can see that there's a downward trend. You know, it goes down, and so it seemingly maybe worked. Just so yeah, as I was saying, there's a downward trend in figure 1 that compels us to believe that maybe the tax on cigarettes worked, right? So, but we're not sure, you know, because there's also a downward trend in the rest of the US. This is an average. The dotted line in figure 1 is an average of the cigarette sales of all the US states, the rest of the US. So we are like, maybe it worked because we see that the downward trend for California is like more, like, you know, more downward, more steep in a negative sense. But it's hard to make the claim, the causal claim, because we cannot see the counterfactual California, the alternative California, in a parallel universe in which Proposition 99 was not implemented, we cannot see at California what would have happened. But the whole point of causal inference is that one. The idea behind the synthetic control approach is that the combination of units often provides a better comparison for the unit exposed to the intervention than any single unit alone, or an average of those units. In this case, as we see in this figure, we would rather have something like what we're going to see in figure 2, sorry. But before we get there, a few other concepts. What is the synthetic control? If you want to learn what the synthetic control method is in any of the papers, just type weighted average, and it will take you right to the definition. That's the best way to find the definition in these papers. Sometimes it's hard to find, surprisingly. But the synthetic control method is that. A synthetic control method is a weighted average of the available control units. That's the definition. I'm going to highlight this in other color, possibly pink, because it's very important. A synthetic control is a weighted average of the available control units. What does that mean? The synthetic control method makes explicit the relative contribution of each control unit to the counterfactual of interest. Right? What is the relative contribution? Well, if we go to the table, let's see. Here, state weights in the synthetic California. Of figure 2, synthetic California is a dashed line. We see that Colorado has a weight, Connecticut has a weight, Montana has a weight, Nevada has a weight, and Utah has a weight. Somewhere in the paper, if you see a map of the US, maybe it's relevant, why not? Somewhere in the paper I remember that they mentioned that it's interesting that Nevada and Utah had such big weights. Like, let's see the paper. So it's Nevada, Utah have the biggest weights, respectively. And they are just next to California. This is a good sign because we can sort of like see, hey, our weights after all make sense. It's not like Florida ended up being part of it. It could have been, but it's nice to see that when you apply the method, you realize, oh, hey, the weights make sense. The method actually makes sense of reality. It makes sense that the economies of Nevada and Utah can resemble in many ways the economy of California compared to at least other states in the US. So it's nice to see that the method, as it says here, makes explicit the relative contributions, this probably should be again in yellow, right? Makes explicit the relative contributions of each control unit to the counterfactual of interest, right? And the similarities or lack thereof between the unit affected by the event or intervention of interest and the synthetic control. Blah, blah, blah. This is a little obscure, the way this sentence is written. But I think that's the straightforward idea. If we take the mean of all the US states, we get this. And it's not a very effective comparison, The idea behind the synthetic control approach is that what is better? A combination of units often provides a better comparison for the unit exposed to intervention than any single unit alone, or perhaps even a very, I want to say a dumb average, like you just take like a whole set of units and average them, but that's not systematic. And the vision of the synthetic control method is to systematically choose control units and make explicit the contributions. You could perhaps say arbitrarily, really sorry about that, just yeah, don't make these videos when you're a little sick, sorry. But I have to, because I want to release this week. So yeah, the vision is to make the contribution of the control units explicit and the choice systematic. Those two ideas are very important. You could say, let's take the average of all the states in the US. Too arbitrary and in the end not very effective, as you can see here. Or you could say, hey, I'm an expert in the US and I'm going to choose Nevada, Utah, Arizona, Oregon, and who knows what else. Yeah, and who knows what else. But you would have to get lucky. And it would feel like a little like cherry picking, perhaps. I don't know. Arguably, it would be too arbitrary to just like choose them. And that's, I think, one of the things that the synthetic control method came to do, to make the choice of control units a systematic one. You follow a method, a process that tries to arrive objectively at the best possible synthetic control of your treated unit. And that's how you create the counterfactual, right? Alright? Yeah. The relative contribution of each control unit to the counterfactual of interest. Yeah. So I think that's the definition. We can go ahead a little with the code. What do we do next? Well, we need to learn how to use the package. Help synth. What did I do here? Like I typed help synth. And so I get here the help file for the synthetic control package. The first thing that we must do to run this is, let's see. So the synth library offers a preparatory function called Dataprep that allows the user to easily create all the inputs required for synth. So before you run the synth model, the synth function, you need to prepare your data in a way that you have the inputs properly formatted. Well, obviously you need first to your dataset, but we already saw the dataset, how it looks. This is how the dataset looks. You see, we have the units and the predictors and the years. That's pretty much it. So for a given year, there must be a corresponding unit, the state in this case. And horizontally, we have here sick sale, income, logged income, in fact, the logarithm of the income, and the sales of beers, and the population age, and the retail price of cigarette sale. So we have that, and we must use the Dataprep function to get a few matrices that I'm going to show you. It's going to be more clear once we get perhaps the output of Dataprep. All right. I want to move this. Okay, so Dataprep out. You know, I'm going to be using a different convention, like underscores for my libraries. Dataprep function. The first argument of Dataprep is the data, pretty much. California data frame. The second argument is the predictors. Which are the predictors? Well, so in principle, we have to go to our paper first, right? The paper we're trying to replicate. The predictors, the GDP per capita, the logarithm of it, all right? In our data set, that's called L-line income. So we go here, L-line income. We also see that the percent aged 15 to 24. That's age 15 to 24. The retail price of cigarette packs. So, retail price. Those are our predictors. Then we need, well, the way I'll do it is, yeah, we can define the special predictors as well right away. Let's do it in that order, right? Makes sense, right? After the special after the predictors. What are the special predictors? So it's pretty much a list of objects identifying additional numeric predictors and their associated pretreatment years and operators. It's just a help function for those cases in which you are going to have certain predictors applied to specific years. That's all it is. There's nothing special about them other than perhaps incomplete data sometimes, or maybe you figure that there's a better balance in the end if you apply the special predictor for very specific years. So the way we do that is with a list object that has other lists. In fact, the first argument of the list or item of the list is, in this case, 6 sale. Then we add the year, the explicit year. In this case, it's first we go with 1975. When it's a single year, you can just do it like this. But this also takes ranges, so it could be like 1980, right? Like this. But or a sequence in R, if you know about those, like every 2 years or something like that. But in this case, it's pretty straightforward. It's just this, and the last argument is the operation. You have to put it like this to follow the format of the package. So that's how you go about it. We do it for the other years, 1980 if I'm not mistaken, and 1988. Right. Then we go with the dependent variable. The dependent variable is in this case 6 sale. You know, this also takes a numeric. It's a scalar identifying the column number. Could be. That's how it's often applied. But I like readable code, so we are going to do a column name character string. That corresponds to the numeric dependent outcome variable. The outcome variable, 6 sale. We're going to do it that way. Then the unit variable. What's the unit variable? Well, our units are the states of the United States. And the unit variable, in fact, as a requirement for this package, must be a scalar identifying the column number or column name character string associated unit numbers. The unit variable has to be numeric. So what does that mean? I must say a state. I can type here a character to identify the column, or I could type just like perhaps number 1, because that's the first column of my data frame. But again, I like readable code, so we're going to do a state. But the units must be numeric. That's a requirement for the method. The unit variable has to be numeric, like the actual variable has to be. In this case, it was parsed as an int, which is fine. Okay. The time variable, same thing. We're going to type year. We could type 2, but I prefer year. More readable. And here comes the treatment identifier. You know, usually people often do like 3, because if you go to your dataset, California is number 3, like as you can see here. California is number 3. However, I prefer to do California. However, if you type here a string, as it says, if a character is supplied, a unit names variable also has to be supplied to identify the treated unit. This one, it seems that it's optional, but in this case, it's going to be absolutely required because we are providing a string here. Therefore, we must do names variable, which is a state name. Obviously, the names gotta be unique, otherwise we would run into a problem. In this case, the state names of the US are certainly unique. So, state names. Alright, but we were here. The controls identifier. Which are the controls identifier? If you know a little R, we can make an operation here that can be helpful to list all the controls identifiers. Let's see, I'm going to print this. We could do, for example, like California data frame. We can do numbers, but again, I like strings. It feels more readable, so I'll stick to that. We can do all the states minus whatever is the index of California, which, you know, like, it should be like California data frame, state names, minus whatever is California. If we select this and do Command Enter in a Mac, on a Mac, we can run this little bit of code. Give me a second, I'm sick and I need to take a... Yeah. So we'll run this little bit and it takes away California. This is the way you take away California, but we need just identifiers, right? So we do this, we select this, and there you go. We have all the states except California. California would have been here, right? Be careful, you gotta put this here inside, right? And then take the unique names. Okay. I'm going to put this line. I think this is fine. Okay, controls identifier. Time predictors prior. What is time predictors prior? This one is a little bit confusing because it's very similar to time optimized SSR. But it says time predictors prior is a numeric vector identifying the pretreatment periods. Everything before the intervention time, over which the values for the outcome predictors should be averaged. You know, let's not complicate our lives. You can pretty much get a good application of the method by just sticking to your pretreatment period. So we're going to do 1970. If anyone has comments about this, I want to hear your thoughts. But I think for learning purposes, it suffices to say, okay, let's just go with the pretreatment period, right? Time optimize SSR, yeah. Optimize whatever is there in the pretreatment period. Up until the intervention time of 1988. The time plot. This is a vector identifying the periods over which results are to be plotted with gaps.plot. Gaps.plot is a utility function which we will be in fact not be using because I want to make it more illustrative. But you would do like the whole of your dataset, right? If you type like California data frame here, unique, the dataset goes from 1970 to 2000, okay? 1970 to 2000, and that's it. There you go. That's how you prepare your data in a very readable way for the synthetic control method. Let's run it. There's an error. Unused argument. For predictors, there's something of Airline income, age, time predictor prior is an unused argument. How come? I wonder if this was an issue. Maybe you catch my error faster than me. Let's see if this is typed correctly. There's a comma here. There's a comma here. Yeah. Error in Dataprep. Unused argument. Time.predictor prior. Maybe I typed wrong that. It's time predictors prior. Yeah, we were making up one argument. Undefined columns selected. Airline income, age 15 to 24, reach price. By the way, I think we missed beer. We should have put beer there. Anyway. Unexpected. Missed a comma. Undefined column selected. Where are we getting that error? Our data frame seems to be fine. I wonder if... Undefined column selected. Let's see. I'm thinking, where's the mistake? Is the mistake in our dataset? Could it be undefined columns selected? Airline income. Oh, here's the mistake, you know? It was airline income. Check out for typos. I have an extra n before the m. Alright? Yeah, perfect. So, we got our Dataprep Output object, which I want to go over with you. Hi, I'm back. You may have not noticed, but I took a very long break, several hours, because I'm a little sick today, but gotta get done with this, alright? You know, so where I left was right after we fixed the issues here with these parameters, and so we can run this, right? And we get, well, you can see here that it ignores a few of the missing data, like beer, for example, is a variable that has like a lot of missing data at a lot of points. In theory, you would be able to avoid this if you put beer here as a special predictor and specify the exact years for which you have data, but it's fine. It's just going to ignore the years for which beer has like no data. So that's fine. But anyway, so I left here, like this runs successfully. You can see the object here. It has all its attributes and all of that. The next step would be to insert the Dataprep object, right? The whole point of this Dataprep object is to insert it, you know, like somewhere here in the help file. It says you put the Dataprep object in the Synth function, and then you run your model, and you get your model, right? But before we do that, I would like to spend from 5 to 10 minutes. It sounds like a lot of time, but it's going to be very important and fruitful and useful. I want to spend some time exploring this object, this Dataprep out object. You gotta learn what it has, because it's going to be very helpful for you when I was first learning how to use this method, I reinvented the wheel a lot of times with the outputs because I didn't notice all the useful things that this object actually prepared for you. That's the whole point, right? So let's check it out. So here we have like the usage of the Dataprep function, the arguments, and then we have the output values. Some are more important than others. H0 is a matrix of controls predictor data. Yeah. So, let's show you H1, a matrix of treated predictor data, right? Let's move my face here. So, here you have a matrix of treated predictor data. And in the paper, that corresponds to this little table. You have a matrix of treated predictor data. If I'm correct, this should be the average, right? So the treated predictor data. All variables except are averaged. Yeah, right. All variables except lagged cigarette sales are averaged. So this is an average for the 1980 age period. You know, I think I made a slight mistake here to replicate this perfectly. I want to highlight this like a lot. These are average for the 1980 age period. Apparently beer consumption is averaged for this other period. Anyway, so the average is very close, I think, 10.031. It's not exactly 10.08. Most of these numbers, if you pause the video and take a close look at these numbers, you're going to realize that most of them are very close to what you see here. For the treated, like real California is like it's 1 because 1 means like treated, right? So you can see here, these are the averages. They are close, and the issue they are not exact is because in time predictors prior, we did from 1970 to 1988, where in fact it told us, like here, this was like identifying the pretreatment periods over which the values for the outcome predictors should be averaged. You know, this replication is very close to perfect, except for these small nuances. In the interest of time, I'm not going to play too much with getting the averages for this predictor means exactly right, because in fact they are good enough like this. And I want to teach you how you can replicate most papers, like, you know, like really well. Like it's negligible, like these small differences. When we get our figures, you're going to realize that the numbers are like very, very close. So in this case, in the interest of time, we're going to just stick to the basic application of the method, which is just stick with the same time frame for all this stuff here, these parameters, these two in particular, which are like the important ones, right? But this is what this object is meant to give you. I wanted to show you that. X0 does the same thing for the predictors data, for the controls. But it gives you, like, this looks a little more confusing than it should, but the reason is that there's not enough space here. All this is like a long horizontal line here, like of the controls. As you can see, California is missing, and what's below is just like the continuation of that, right? So let's focus on the actual thing here, right? It's a matrix in which you have as rows the predictors, right? And the columns are like the controls. Now, this is not what you have here, right? This, if you take the average of the control states, you will get this column, right? if you take the weighted average, we haven't gotten the weights yet, but we will, then you will get like this, right? You would sort of like take the linear combination of the columns, right? The weighted average of the columns. You get one last column, which, if it's the weighted average of the synthetic weights, you will get this column, and if it's just the average, you will get this column. But that's what this object is meant to be about, right? And these are not that important. You know, you can explore set 1 and set 0 a little. You can read what these are about here, but I want to skip this because the real meat is here. Y1 plot and Y0 plot, which for some reason that escapes my understanding, it's the same as just Y1 or Y0 plot. Like, what I mean is like Y0 plot is the same as Y0. Like, for some reason it's the same thing, right? So let's just choose Y0 and Y1. And what is the Y in the causal inference literature? The outcome stuff, the outcome data. Y0 means the outcome data for the controls, and Y1 means the outcome data for the treated. And you know, this is just data preparation. We still don't have anything related to a synthetic control. This is just data preparation. Based on what we inserted, it gives us that. Like, for example, Y1 is just the outcome data for California. For every year, 3 is California. And Y0 is for all the controls, which I so much wish they fitted here in one line, because this print statement looks confusing because it doesn't fit. But it's just this, right? 1, 2, 3 skips, no, 1, 2 skip 3, which is California, 4, 5, 6, 31, and then continue here, 32, 30, blah, blah, blah. But here you have a matrix, you know? And this matrix is it's going to be very useful in a little bit, because I also want to show you later a resource in which we can visualize what's actually happening, you know? Once we get this matrix, perhaps I can show you now. I don't see why not. Give me a second. So here, right? Give me a second. The reason this matrix is so useful is because it's useful for learning. When I was learning the method, I wish I had looked at it that way. This is our matrix. Imagine the red is Arkansas, the green is Alabama, the blue one is Colorado, and we can keep going for all the control units. But A, B, and C are weights, you know? A could be the weight for Arkansas, B could be the weight for Alabama, and C could be the weight for Colorado, you know? It could be that Alabama has a 0 weight, I don't know. Arkansas could have like a 20% weight. And C could have a 90% weight if these were all the only controls, right? You gotta sum up to 1. But, or we're going to be using more controls, so assume it's like a weight that is actually smaller. They're usually smaller. But anyway, the point is, you're going to make the matrix multiplication, which is a linear combination, which is pretty much every weight multiplies every control unit, its respective control unit, and you sum that up, and you get here your synthetic California in pink here. That's the visualization that I want you to have. And it's useful to know that Dataprep Out gives you the data in this format, because then when you're doing your analysis later on, more sophisticated analysis, you want to know that you already have the data very well structured in a way that you can easily manipulate for your synthetic control analysis, right? Now this is taking more than 10 minutes, but I think that's it. Keep in mind these two attributes or properties of this Dataprep Out object, which we just got, because we're going to need it later. All right, now the real meat that we have been waiting for since we got started with this video tutorial. we want to use the synth function. Okay, let's do it. Synth out is going to be the variable where I store the result, the model. So synth, the first parameter of synth is Dataprep object. What's that? Well, the Dataprep out. And there are other parameters here that people sometimes use. We are just learning, so let's stick to the basics. This is all we need. We run the thing, and we're going to get our solution. Here's a print statement with the solution weights, which is the most important thing. These weights are the core of the method, right? And what did I just told you, you know? I told you that here in this object we have the y0 plot, or just y0, it's the same thing, right? Which is like, I really want to look as much of, see as much of it as I can, right? So we have here like this matrix, right? And what I want to do now is multiply it by the weights. So I multiply by the weights. Synth out, which also we're going to explore a little, like it has like a few attributes that you should play with. It's the best way to learn to use a library properly. Like, take a look at the outputs and the attributes of the outputs. What is it giving you? So it's giving you the solution weights. Like the solution weights alone, if we just run solution weights, is that, the solution weights. But the interesting thing is what happens when we multiply it with the control units in the way that I told you a moment ago, right? What was the way? This way. My face and these comments are blocking everything. Okay, so we do the matrix multiplication, which is what we're about to do here, right? Let's do it. Wow, we got an error. Well, why? Because matrix multiplication in R uses this operator, percentage sign, asterisk, percentage sign. And it didn't work. The reason it didn't work is because I was selecting one percentage sign. And when I do that with command enter in on a Mac, it only runs like that a little bit, but I want to run the whole line. For that, I only place my cursor there and do that. Boom. We get this matrix. Ignore the title here, because what this is actually is the outcome data for the synthetic control. And let's visualize it, right? I'm going to do it like this. Plot. I'm going to leave this here like synthetic California, which is control units matrix multiplied by weights column, or matrix, which is just a column matrix, right? Weights column, right? I want you to really think about it this way. Right. By the way, very quickly, I wanted to mention this resource. I want to give credit to this guy because, so type causal inference for the brave and true by Matheus Facuri. This guy from Brazil has this open source resource in which he explains the method very well. And the first time I got the idea of the method to learn to think about it that way was when I visualized it here. Because in the papers, they speak of matrices, but, you know, it's very nice how he illustrated it here. He has these, like, explanations that are very visual, and I think really make you click this matrix multiplication way of thinking about it, you know? And he explains very well the optimization process as well. So check it out. He also just recently published a book. This is open source, but he also published a book called Causal Inference for Python by Matheus Facuri. published very recently in 2023. I highly recommend it. It's a very good resource in causal inference. Anyway, so yeah, we were about to plot this matrix multiplication, which is the synthetic control in the end, a weighted average of controls, right? And we're going to do it from 1970 to 2000. I think those are the years, right? Yeah, I'm missing a comma here. There you go. That's our synthetic control, but that's not very clean. Let's do it with a line. That's a little better. I recommend doing it with a dashed line. How do you type the dashed line? I have it here. I'm cheating right now very quickly. It's LTY. Yeah, always forget how to do it. LTY dashed. That's the synthetic control. But obviously we want to actually take a look at the whole thing compared to the real California. And where do we get real California again? Remember, I told you, take advantage of the Dataprep object. Y1 plot, or just Y1. Y1 is just, as I told you, a matrix of the 3-red unit, which is only California, of course. So 3, California. So we run this lines function, and we get it. You see? That's a figure. You know, it would be nicer if the Y limb was closer to the one of the paper, from 0 to 140. You see? And it's just like the figure of the paper. I'm not going to bother with the caption, with the labels, with the legend, even with the vertical line, I think. Well, I can add that, yeah. Okay. Yeah. Oh no, wait, wrong year. Oops, yeah, that's right again. Yeah, so this is the replication of the figure. Congratulations. If you make it to this point, you are ready to replicate the paper. At least the core of it. Because I also want to do the gaps plot and even this plot. Yeah, a few of these plots. I think it's going to be worthwhile. All right, so that's how we replicate the synthetic control in the seminal paper. And what else? Yeah, the gaps plot. How do we go about the gaps plot? Well, there's a function called gaps plot. I recommend you to learn how to use it. But I also recommend you to understand, you know? Figure 2. Real versus synth, right? Gaps plot. You know, if you think about it, the gaps plot is nothing more than... Let's store this as a... Synth California. It's going to be like this multiplication, right? But the gaps plot is nothing more than real California minus synthetic California. If I'm not mistaken, is that way, right? And the real California is, which one is real California? Well, it's the Y one, right? This is our gaps plot, if you think about it. Gaps. Right? Let's plot the gaps. Plot 1970 to 2000 on the gaps. Again, type L. A B line. How do we do the horizontal line? AB line. That's AB, yeah. Okay, yeah, AB line, H0. Yeah, this is the gaps plot, as you can see here. You know? The gaps plot, which is the real California minus this is the difference between real California and synthetic California, you know? Again, so real California had a more negative trend than synthetic California because real California suffered the tax on sales, right? Synthetic California didn't. So the beauty of the gaps plot is that we can appreciate how the synthetic control is resembles very closely the real one up until the intervention time. After that, it goes downwards, we can see the effect. The gaps plot pretty much measures visually the effect. For every year we can see the effect or the estimated effect, right? And that's the gaps plot. So I estimate that our video tutorial is about 1 hour long by now. I want us to recap a little with the functions. I try to make the code as clean as possible. I'm going to publish it on GitHub. First, you prepare the data, run the model, and then take advantage of the outputs to get the synthetic outcome data and the gaps, which is just a subtraction, very straightforward. What we are missing to replicate right now, so far I think this figure is just an average, right? So I didn't replicate this one, but I can add code for that one as well when I publish it to GitHub. But we replicated this figure, which is the essence of the paper, the synthetic control. And we replicated this figure, which is another visualization of the synthetic control compared to the real California, right? Synthetic California versus real California is what we did on this video. And right? What we are missing is these figures, the placebos, you know? The placebos are we run the synthetic control for the control units. That's what the placebos are. We put back California in, and we take Alabama. We run the method for Alabama. We put back Alabama in, and we take out Arkansas, and we run the method for Arkansas. We put back Arkansas in, and we do what? Colorado out, run the method for Colorado as if Colorado was a treated unit, put Colorado back. We do that, and the idea is that we compare how extreme the results for California are, you know, how not random they are. And the beauty of the method is that we can visualize very well that, wow, hold on, indeed, it seems that the sorry. Yeah, so indeed it seems that the results for California are not random, you know, that they measure later, obviously, it's something you have to measure, the statistical significance, but this is a visualization that intuitively illustrates why the method is so powerful. So we're missing these placebos. This visualization is also about that, which I'm going to explain in a next video. I think this is going to take 2 videos. We're missing a placebo in time. Apparently they didn't do this in this paper, the placebo in time. At least they didn't do a figure with that one. I can't see it. Where's the placebo in time? Well, the placebo in time is in another paper. It's very common. There's this other paper which is about estimating the effect of the reunification of Germany, the effect of that on the GDP per capita of West Germany. I also want to replicate this one, but in any case, in this paper they talked very well about the placebo in time. Let's see, because reunification happened in 1990, but the placebo in time is, hey, let's assume that the intervention was in 1875, right? The placebo intervention. And then we run the method and we test whether there's still a good fit, where the synthetic control is able to simulate the real one still for a number of years. And ideally, the effect is appreciated only after the intervention. They start differing, In this case, the effect is still like a little less pronounced, but you can see here that kind of like around this time, there was a difference, like they started to differ. But most importantly, you want to see whether this is still a good fit a little years after the intervention, placebo intervention. So we're also going to do that in the next video for California, even though it's not illustrated in the original paper of California. And this figure I also want to do, which is pretty much another way to visualize the information, the same information, in this figure. This figure has a lot to do with this figure. It's pretty much the same measure. They just did a histogram here, but they prefer to illustrate it this way here. All right. So I hope the video is useful. Again, I'm going to share this code with you. I try to make it as readable as possible. I try to speak out loud my thoughts process as much as possible. I try to teach you about the objects and their attributes as much as possible. And I struggle a little bit. First, because I'm a little sick. Sorry about that. And second, because I'm also practicing how to apply the method. And a good way of practicing sometimes is by sharing it with others and teaching. And a good way to learn is observing someone struggling with a live video. I'm going to try to make this video with as many chapters as possible so that you can skip certain parts and understand the structure and just get to the point if you just need to watch this very fast. Alternatively, you can also just speed it to like twice the speed and put on subtitles, right? And because I'm not a native speaker, maybe that's useful to play the video at twice the speed and watch read the subtitles, right? I'm sure it's going to be. I've done it with videos of myself, and I think it's like the right speed to watch my video tutorials. Thank you for watching. If you have any comments, feedback, things you wish had been explained about the method, please don't hesitate to reach out. I want to learn what the audience wants, and I'm going to try to my best to cover this whatever questions you have in the next video and do it better, because I hope every video is better than the previous one. In this video series, don't subscribe, because we're going to replicate a lot of other papers that apply the synthetic control method, such as the one of the Basque Country and the one of West Germany. Okay, so that's about it. Yeah, that's it. Maybe I could invite you to check out our website. Perhaps by the time you check it out, we're going to have more interesting stuff to show you. But our channel is called Causalify for a reason. We are causalify.com. And we're creating a SaaS tool, software as a service tool, that will allow you to use the synthetic control method without code. If you want to replicate California, well, you just click here, wait a few seconds. Here, I define the special predictors and all of that. And we're going to make it faster by the time you check out our website. But anyway, so here you can replicate also the synthetic control. There are other examples here as well. And yeah, this is what we did today with code, but you can also do it without code, as we are creating this platform to use causal inference methods very fast and easy. Thanks.